All right, everybody, let's get started. So we're looking at section 1.2 today, which is going to be all about biomass and energy. So just a heads up with what's going on the rest of the week. Tomorrow you're going to be taking a look at section 1.3, and that will be the end of chapter 1. So following that day on Thursday, you'll have a day to review. And then we're looking at a chapter 1 quiz. So I'm not going to put it on the Friday because I know if you have any questions, um, I want to make sure that we get them all answered. And I'm also not going to put it on the Monday because I want to give you a day to kind of clear up any issues you might have. So that means we're looking at a chapter 1 quiz on next Tuesday. All right, so that's what we're putting that in for. So next Tuesday. But let's get going with today's stuff. So this is one of my favorite topics pretty much of all time, photosynthesis. One of the craziest things ever is the fact that plants can just chill outside and eat the sun. I mean, if you don't think that that is absolutely nuts, something is wrong with y'all. These plants sit outside, don't even eat any food. They just absorb some nutrients from the soil and then just munch on the sun all day. And not only that, they eat the sun, but they also require something from us. They take this poisonous carbon dioxide out of the environment and exchange that for life sustaining oxygen. It's unbelievable to me. So, photosynthesis is all about that. It's changing this solar energy, so energy from the sun, into chemical energy that the plants can use. And you might be wondering, oh my gosh, why are all plants green? It's because there's something called a pigment. And a pigment is pretty much anything that gives something its color. Plants have something called chlorophyll. And you'll notice that most plants are green because of this pigment. So that's the real key to making sure that all plants are green. All right, this YouTube link, if the teacher could just click on this YouTube link, it's a really good demonstration about pretty much everything that's happening in photosynthesis. So upon conclusion of this, if you could just go to that YouTube link and we can go that way. So there's a chemical reaction, and we know from chemistry that on one side, our left side over here, we have our reactants. So these are our starting things. So these starting things undergo a chemical reaction using light energy in order to get our products. So we have our reactants being exchanged from light energy into our products. And some of you might be able to pick out some of these things that you might be familiar with. So CO2 we know is carbon dioxide, and we know that H2O is water. So that means for photosynthesis to happen, we have carbon dioxide and water. That makes sense. They take the carbon dioxide out of the air, and plants definitely need some water as well. They combine that with some solar energy, and then we get the oxygen, O2, which we already know about, but then we get something else. This something else is the energy. It's called glucose, and that's what plants produce as energy. So these are reactants, these are our products. All right, just another YouTube clip if you could at the end, that'd be great. Please make sure you copy this in. If I am going too fast at any point, if the teacher could just pause it, that'd be great. This formula, though, I will tell you right now, if you could put a star, circle it, highlight it, whatever you got to do, you are going to need to know both the word and chemical formula for photosynthesis. So you're going to need to know what the chemical symbols mean. So you should know that CO2 is carbon dioxide. You should know that C6H12O6 is glucose. And you'll also need to be able to provide the word and the chemical formula for photosynthesis. Okay. The cool part about photosynthesis, like we said, is that not only does it use solar energy in order to produce oxygen, but it also takes out the poison that we produce. So when we breathe, you obviously give off carbon dioxide. So whenever you breathe out, you're giving off carbon dioxide, but you're also giving off some water. And you might have noticed this if you ever fog something up. So if you go up really close to a glass or a mirror and you breathe on it, you'll notice that it gets a little foggy. That's because there's water vapor coming out of your mouth. So every time you breathe, you're not just breathing out carbon dioxide, you're breathing out water, which is interesting because those are the exact same things that we need for photosynthesis. So these two things are incredibly complementary, is what we say. So this little paragraph here, give that a highlight. I'm not sure if it's written in, I cannot remember. If it's not written in, please copy this in. And if it is, you're going to want to highlight this. It means these things are complementary. They're reciprocals of each other. So they can't work without one another. We can't have photosynthesis without cellular respiration. And we can't have cellular respiration without photosynthesis. Because if you take a look at the formula up here, these in cellular respiration are our reactants. But in photosynthesis, we find them on the other side of the arrow. That's when they're our products. And the same thing over here. Carbon dioxide and water were our beginning reactants in photosynthesis, but in cellular respiration, they're on the other side of the arrow. So we literally just flip-flop this thing around and you get photosynthesis. So just like the other one, you're going to need to remember the chemical formula for both photosynthesis and cellular respiration. But please keep in mind, this one is just the flip-flop of photosynthesis. Okay, trophic levels. You've probably seen food chains or food webs somewhere throughout your education. This is no different. The one thing that you need to remember as you copy this down is the arrows. Everybody kind of gets a little bit tripped up about the direction of arrows. So once you're done copying that down, I just want to tell you one thing about the direction of arrows, so I'll give you a sec. We always want our arrows to go in the direction of energy flow. So if you can write that down, you can just write arrows go in direction of energy. So if you just write that down, arrows go in direction of energy. So think about it. Energy starts from the sun, gets passed to the plants. The herbivores come along, eat the plants, and they get some energy from that. And then we get a bird, it comes along, eats a little insect, it gets some energy from that. And then our top carnivore comes on, eats this thing, and gets some energy from that. So energy is passed up the food chain, which is why when you're drawing arrows, you always need to show which way energy flows. And it's always going up. So we always start every food chain with the sun. We just don't include it when we talk about trophic levels. Our first trophic level will always, always, always be plants. So no matter what food web you are looking at, your first trophic level has to be a plant. I will say that again because that's important and something you should make note of. Your first trophic level is always a plant. All right, and then as you move up the food chain, we get to the second trophic level, the third trophic level, the fourth trophic level, the fifth trophic level, and as many levels as we have, we just keep changing the number. Okay, biomass. Biomass is just if we put all of that species on a scale, how much would it weigh? That's basically what biomass is. It's how much all of them weigh together. So if we looked at all of the antelopes in an area and we gathered them all up and we said, all right, antelopes, get on the scale, whatever that number would be, that would be the biomass of antelopes. But the thing is, biomass, it always, always, always is the largest when we talk about primary producers, aka plants. Plants have the most biomass. So things like grass, even though it doesn't weigh so much, there's so much of it that if you took all the grass in an area, put it on a scale, it would destroy the number of antelopes or the biomass of antelopes. It weighs way more. It's so plentiful that primary producers always have the most biomass in an area. Okay, so as you move up, we said primary producers all the way down here will have the most biomass. The next one will have a little bit less biomass, but still quite a bit. And then as you move up in trophic levels or up the food pyramid, the biomass gets smaller and smaller and smaller. So if you think about it, things like great white sharks are really heavy, but there's not too many great white sharks out there. And that's why their biomass is so few. But if you think about things like minnows or very small fish, yeah, they don't weigh so much, but there's so many of them that their biomass is huge. So the lower you are on our food chain or our food web, the more your biomass is going to be. So your primary producers will always have the most biomass, and your top carnivore will always have the least. Okay, 10% rule. So let's take a look at this. When we talk about energy transfer as we move up a food chain, we start off with grass, as always. So let's say the grass has 1,000 units of energy. Ooh, that is some good grass. Now, the jackrabbit comes on and he says, oh my gosh, I got to get me some of that grass. Starts eating that grass. Well, it's definitely not going to get all 1,000 units of energy of that grass because, well, and we're going to get into it, there's a huge number of reasons that you don't get all the energy. Think about yourself when you eat a piece of fruit. When you eat a piece of fruit, there's energy in that entire apple. So we're saying there's energy in the seeds, there's energy in the stem, there's energy in the core, but you don't eat that. You probably just eat the really good tasting part, but there's lots of energy in all these other places. And just like animals, they don't like all the food they're eating as well. So we always lose some energy as we move up the trophic levels. But there's 10,000 energy units in some grass. When the jackrabbit comes along and eats it, it gets on average 100 energy units. So it actually gets about 10%. So as you move up to get from the 1,000 to the 100, what you do is you just divide by 10. So let's say this weasel comes along and it says, oh my gosh, a great looking jackrabbit, I got to get me some of that. So it eats the jackrabbit, which has 100 units of energy. As we move up the trophic level, we divide by 10 again, and now we're at 10 energy units. And then the great horned owl comes along, sees this weasel, eats it, and now it's going to be divided by 10 again. If something came along and ate this great horned owl, well, all we'd have to do is take how many energy units are in that and divide it by 10. So every time you move up, you divide by 10. Let's take a look at an example. Okay, so we know all about this 10% rule. 10% of energy gets transferred from one level to the next. So if we start with 140 in the grass, rabbits come along, we divide by 10. Now we're at 14. We divide by 10 again, we're at 1.4. And if you divide by 10 again, now you're at 0.14. If something came along, you just divide by 10 again. And if something came along after that, you divide by 10 again. Every time you take a step, you just divide by 10. So why does this happen? Well, I started talking about the apple, but things like herbivores, they might not eat all the parts of the plant, might not like the stem, might not like the flower, and not everything that is eaten is digested. So we don't have a perfect digestive system. We can't absorb and extract all of the nutrients out of everything we eat. So we don't get all of the energy that we're eating. And basically, we lose a lot of energy as heat from the body's organism. So when you eat something, it doesn't just go right to sustaining you. Lots of times we use that as immediate heat production, depending on where we are living or the setting or the ambient temperature. So a lot of things go into that. Okay, these next two definitions are incredibly important and something that you're definitely going to want to know the difference between. So the first one, and you know what? You guys aren't going to listen. I'm going to let you copy this down. So just pause me and then resume me when everyone's done copying. Ready and pause. And resume. Okay, so bioaccumulation. Basically, bioaccumulation is what happens if an animal just kept eating poisonous stuff. And you're thinking, well, why would they just keep eating poisonous stuff? Lots of times when you're eating poisonous stuff, you don't know it's poisonous because it tastes just like regular food. So let's say there's a cow, and this cow starts eating the grass around it, which has been covered in an insecticide, which is basically just like a pesticide. And it's poisonous to the cow. Now, the cow doesn't know because there's a very, very small quantity of toxins in the grass, but the toxins aren't so good for the cow. Now, cows' bodies are pretty good at fighting off a lot of things, but they're not so good at fighting off poison. So if this cow keeps eating and eating and eating this grass, well, eventually it's going to get pretty sick. That process is called bioaccumulation. It's when our bodies absorb toxins, aka poison, at a greater rate than we can get rid of them. So if you keep eating poison at a greater rate than your body can naturally get rid of it, eventually you're going to get toxins and poison building up in your body, which is going to make you sick. Now, if you ate this grass very, very slowly, your body might be able to get rid of most of it, but cows like to eat, and they like to eat a lot. So there's a really good chance that they would have bioaccumulation happening, the process of getting more and more poisoned over time because our bodies can't keep up with how much poison we're putting in our body. Now, that's very, very different than biomagnification. Biomagnification is something very, very interesting. So let's take a look at a really, let's say a small rabbit. So the rabbit sees some of that grass that cow is eating, and it gets super stoked because it takes a look at it and it says, I got to get me some of that. And that's exactly what it does. So it gets some of that grass, starts eating it, and now this bunny gets sick. Not so good. So when this bunny gets sick, it starts getting really sick. So let's say it has 50 units of poison in its body. That's a sick bunny. But what happens is a fox comes along and it starts eating this bunny. Now we know that not all of those toxins are going to get passed to the fox, right? We talked about the 10% rule. So if it had 50 units of poison in it, well, we might get somewhere around 5 units to this fox. So not too much. But what actually ends up happening is because the fox doesn't just eat one bunny, it eats a lot of bunnies. It'll definitely eat more than 10 bunnies. So because of that, the fox might end up with, instead of the 50 units of poison that the bunny had, the fox might end up with 80, 90, 100, 110 units of poison because it ate so many bunnies. And that keeps happening the farther and farther you go up the food chain. Because now a lion might come along and eat the fox, but it's not just going to eat one fox, it's going to eat lots and lots of foxes. So it's going to have a concentration of maybe 200, 220, 230 units of poison. And if something even bigger than a lion came along, it would eat tons of lions and get more and more and more poison as well. So as you move up the food chain, biomagnification happens. It just means the next organism is going to be even more poisoned than the one before it. And it's simply because it just eats a lot of these poisoned organisms. Okay, this is not always such a bad thing though, bioaccumulation. So bioaccumulation sounds bad. The more toxins you eat, the worse it's going to be because you're going to get super sick. But there's something called the monarch butterfly, a beautiful looking butterfly. It eats milkweed. Milkweed is something that is very, very poisonous to other animals, but the monarch loves it, and it doesn't really affect the monarch at all. So other animals would get super sick if it ate milkweed, but the monarch, that's pretty much all it eats. So the monarch just keeps building up this toxin inside its body until basically the monarch is 100% milkweed. Now, animals are pretty smart because once they've eaten a couple of these monarch butterflies, they know this thing doesn't taste so good, and it's killed a lot of my friends and family. I'm probably not going to eat this monarch butterfly because it's just a walking vessel of poison. In this case, bioaccumulation is actually very, very helpful to the species because people and animals both recognize the monarch's got a lot of poison in its body, not something I want to be a part of, so they stay away. This is a good example of biomagnification, DDT. This was an insecticide that was used very, very commonly around the world, and it was something that wasn't so good for the environment, but it took us a while to figure it out. So it was this brutal insecticide, and all the algae in the water absorbed it. Now, algae is like that green kind of thing. If you left your pool or this pond that's been undisturbed for a long period of time, you might get some algae buildup. Now, it looks gross to us, but lots of small animals love the algae. So they'd go up and they would eat all this algae that's been infected with DDT. Now, we have a bunch of these small fish eating these microscopic organisms. So the microscopic organisms, they get very, very sick because of this insecticide that was in the algae. But then some smaller fish come along and they eat those microscopic organisms. And then some bigger fish come along and they eat the smaller fish. And then we have even bigger fish that eat the fish before it. And at each level, DDT keeps going up and up and up until eventually the birds that ate those big fish started getting very sick as well. It all started from this algae because the concentration of DDT moved up and up and up. So DDT is an excellent example of biomagnification. And here's a really good image of biomagnification. So today, please make sure that you are doing your assigned homework and doing your practice quiz that I have posted online for you. All right, thank you very much. This will be up on the LMS and up on YouTube for you to view at home. If by chance you missed it or you want to review something, please take a look. See you soon. Bye, guys.